The universe is written in invisible ink. We saw the stars for so long, just those points of light, but we were missing the structure, the dark framework that actually holds it all together. That's changed now. Astronomy today has about 30 ways to map that hidden architecture, methods that use cosmic mirages or the faint afterglow from the very beginning. The evidence points to a reality that's stranger than fiction. Most of the cosmos is made of things we can't see. So how did we first detect those ghostly halos around galaxies? And what do the whispers from the Big Bang tell us about the blueprint for everything? The answers rewrite the textbooks. They rewrite our place in all of this. It means living in a universe where the greatest forces are the ones we're only just beginning to perceive. It was a prediction that felt almost philosophical. If mass warps spacetime, then light traveling through that space should bend, not because the light is being pulled, but because the path itself is curved. That was Einstein's insight from general relativity. For a long time, it was just an idea on paper, but then we saw it in the sky, a massive cluster of galaxies, its gravity acting like a lens, distorting the light from galaxies far behind it. This is gravitational lensing, our first way of seeing the unseen. We're not seeing the dark matter itself, we're seeing its signature, its effect on reality. We watch the light from ancient galaxies stretched into faint arcs around a foreground cluster. Those arcs aren't the shape of the galaxies, they're mirages. Smears of light tracing the contours of invisible gravity. By mapping these distortions, astronomers can do something. They can calculate the mass of the cluster. And when they add up all the visible stars and gas, there's a discrepancy. The gravitational pull is much stronger, far stronger than the visible matter can explain. The only explanation is a vast halo of invisible mass enveloping the cluster, a hidden framework of dark matter. This turns the universe into a laboratory. Using gravity itself, the warping of spacetime, as a tool to weigh what we can't see, it gives us a map of the universe's true skeleton, a scaffold built not from stars but from something more mysterious. And if this is how we map the large-scale structure, then how do we probe the beginning to understand why that structure exists at all? The light from those ancient arcs shows us the hidden skeleton of the universe now. But to know why that skeleton is there, you have to go back to a photograph from the very start, a picture from when the cosmos was only 380,000 years old. It's a snapshot of the universe as an infant, this faint microwave glow that fills all of space. That's the cosmic microwave background, and it's our second way to find the invisible framework. You can think of it as the universe's first light, let out when things cooled enough for atoms to form and for photons to finally travel free. For a long time, we thought this afterglow was perfectly smooth. Just a uniform bath of energy, but then our instruments improved. Satellites WMAP and Planck, they mapped this ancient light with incredible precision. And they found it wasn't uniform at all. It was textured. It had these incredibly tiny temperature fluctuations, variations of just 1 part in 100,000. And these aren't random imperfections. They're the most important fossil record we have. Every slightly warmer patch, every slightly cooler spot is an imprint. A frozen ripple from when the universe was a searing, dense plasma. Those ripples were tiny differences in density, the seeds of all future structure. The slightly denser regions had a little more gravity, and over billions of years they pulled in more matter. From those microscopic seeds came galaxies. Clusters, the vast cosmic web, but the pattern of those ripples holds a deeper code. By studying their exact size and distribution, cosmologists can read the recipe of the cosmos. The patterns tell us the total density of the universe. They show the specific ratios of the ingredients. How much is ordinary atomic matter? How much is the invisible dark matter that provides the gravitational scaffolding? And how much is the mysterious dark energy that will shape the future? This baby picture confirms the blueprint. It shows the invisible framework was woven into reality from the first moments. The structures we see through gravitational lensing, the vast halos and filaments, they didn't appear by chance. They grew directly from those primordial whispers imprinted on the sky. So we have a map of the hidden mass today, and we have the original blueprint from the dawn of time. The two match, but a blueprint is one thing. To really confirm an invisible substance exists, you need to catch it in the act. To see its direct influence on the things we can see. Those primordial whispers gave us a blueprint, but the universe is a dynamic place. To see the invisible framework, you have to watch the stars. Picture a spiral galaxy, a pinwheel of light. You'd expect it to move like our solar system. Planets close to the sun whip around quickly. Distant ones like Neptune take a slow, stately journey. The same gravity should govern a galaxy. Stars near the crowded core should orbit at tremendous speeds. Stars out in the sparse galactic suburbs should drift along more slowly. That was the prediction, but in the 1970s, astronomers like Vera Rubin began measuring the actual speeds of stars in spiral galaxies. They traced a rotation curve, a graph of orbital speed against distance from the center. What they found was a silent revolt. The data refused to follow the expected curve. Stars far out in the galactic fringes were not moving slowly. They were whipping around just as fast as the stars near the core. It was as if every star, regardless of distance, felt the same powerful gravitational grip. And that was impossible. If the galaxy's mass was concentrated only in its bright center, the visible stars and gas simply could not provide enough gravity to hold these speeding outer stars. The only explanation was a massive, invisible presence, a vast spherical halo of something enveloping the entire galaxy, extending far beyond its visible edge. This dark matter halo provides the extra gravitational glue. It's the unseen engine that drives the stars in their unexpectedly swift dance. So we have the lensing mirages that map the hidden mass. We have the cosmic microwave background that shows its seeds were planted at the beginning, and now we have the direct testimony of the stars themselves. Their silent, swift orbits telling us that what we see is just the luminous decoration on a much larger, darker structure. This rotation curve is a kinematic fingerprint. Undeniable evidence written in the motion of suns. But if this dark matter is everywhere, shaping galaxies from the outside, what happens when we look for its effects on the smallest scales, inside the galaxies themselves? The motion of stars gave us proof inside galaxies, but to really see the scale of the invisible framework, you have to step back, way back, to a view of the whole observable universe. That's our fourth way of finding the hidden structure, with massive galaxy surveys that map the cosmos in 3 dimensions. For decades, astronomers have done a cosmic census. They use powerful telescopes to find the locations of millions of galaxies. They don't just mark where a galaxy is on the flat sky. They measure its distance, usually by its redshift, the stretching of its light from the universe expanding. That gives a third dimension, depth. When you plot all these points, you don't see a random scattering. You see a pattern, an architecture, vast, thread-like filaments of galaxies stretching across billions of light years. These filaments connect at dense knots where huge clusters of galaxies sit, and between them are immense, nearly empty voids, cosmic deserts spanning hundreds of millions of light years. That's the cosmic web. It's the largest structure we know. Projects like the Sloan Digital Sky Survey revealed this tapestry, but the crucial insight is this. The galaxies themselves, the bright nodes in this web, they aren't the structure, they're just tracing it, like dust motes caught in a spider web showing its shape. The web itself is woven from gravity, the gravity of the dark matter framework. In the early universe, dark matter, responding only to gravity, began to clump first. It formed an invisible scaffold. Ordinary matter, the gas for stars and galaxies, then flowed along that gravitational landscape. It pooled in the densest knots and filaments. So the glittering galaxies we map are just following the contours of a shadow universe. Astronomers test this by creating universes inside supercomputers. They program in the laws of physics and different dark matter models, then let the simulation run for billions of virtual years. When the simulations that include a specific type of dark matter produce a cosmic web that looks exactly like ours, that's a powerful confirmation. We're using the visible universe as a tracer, a luminous dye injected into the invisible river of gravity. By charting where the light gathers, we're drawing a map of the darkness. It reveals a universe where emptiness has a shape, where the grandest patterns are written not in starlight, but in the silent pull of the unseen. The cosmic web shows the shape of the invisible structure. But to see how that shape itself has stretched, you need a ruler, a cosmic ruler placed during the universe's first moments. That ruler is a fossilized sound wave. In the early universe, in that hot, dense plasma, gravity and radiation were fighting. Gravity pulled matter in, radiation pressure pushed it out. That created oscillations. Spherical ripples moving through the primordial soup. They were sound waves moving at a huge fraction of light speed. Then, when the universe was 380,000 years old, it cooled. Atoms formed, the plasma cleared, the photons escaped what we see as the cosmic microwave background, and at that instant the sound waves froze. They left a signature. A slight over-density of matter at a very specific scale, like a single ripple in a pond suddenly frozen into ice. That frozen ripple is a standard ruler. We know its original physical size from the physics of the early universe. For billions of years, as the universe expanded, that ruler expanded with it. The imprint of that ancient sound wave, called a Baryon acoustic oscillation, was stretched across everything. Today, we can see its echo. When astronomers map millions of galaxies in 3 dimensions, it's not perfectly smooth. They find galaxies are slightly more likely to be separated by a specific distance. That preferred separation is the stretched-out imprint of the original sound wave. It's like the universe has a faint, repeating pattern woven into it, and this pattern gives us a geometric tool. By measuring how big this standard ruler appears at different distances, at different times in cosmic history, we can trace the expansion rate of the universe with precision. It's like watching a grid painted on a balloon as you inflate it. If you know the original grid spacing, you can measure exactly how much the balloon has stretched. This technique, Baryon acoustic oscillation, is our 5th way to uncover the invisible framework. It directly probes dark energy's influence. If the expansion were slowing down under gravity, our ruler would appear to stretch one way. But the measurements show it stretching another way, revealing the accelerating push of dark energy. It also gives an independent count of the total matter in the cosmos, visible and dark. This frozen sound wave, a whisper from the first instant, has become our most reliable yardstick. It confirms the dark matter framework and measures the dark energy now shaping its fate. So we've mapped the hidden mass with lensing, seen its seeds in the cosmic microwave background, watched its grip on galaxy rotation, traced its vast cosmic web. And now we've used a fossilized vibration to measure the very expansion it drives. But if dark matter is this pervasive, this foundational, shouldn't it leave other traces? Not just in the grand architecture, but in the light traveling through it. The frozen sound waves gave us a kind of yardstick. But to really map the whole hidden framework, you need something else. Something more subtle, not those dramatic cosmic mirages, but a whisper, a distortion felt across millions of galaxies. That's weak gravitational lensing. Our 6th way to weigh the invisible, Think of it like this: strong lensing, the kind that makes arcs around clusters, that's like looking through the bottom of a wine glass. The bend is obvious. Weak lensing is different. It's like looking through a warped window pane. On a single object, you might not see it, but if you look at thousands of objects through that same pane, you start to see a pattern. A coherent, slight stretching in their shapes, and that's what happens out there. Light from distant galaxies travels for billions of years to get here. And on that journey, it passes through the gravitational fields of all the dark matter, the dense clusters and the diffuse filaments of the cosmic web. Each encounter gives it a tiny shear, a slight stretch, usually less than 1%. Now, no single galaxy's shape proves anything. It could just be odd on its own. But when you survey a huge patch of sky, when you image millions of galaxies and apply statistics, the truth comes out. The galaxies aren't randomly oriented. Their slight elongations align. They point coherently around the concentrations of invisible mass they passed. It's like dropping confetti on a gently curved surface. One piece tells you nothing, but look at all of them and you see they've settled along the contours of the curve. Surveys like the Dark Energy Survey have done this. By measuring the shapes of over 300 million galaxies, they've started to construct a mass map of the sky, not just the bright clusters, but everything. The vast, tenuous dark matter filaments, the empty voids, the whole cosmic skeleton. It's a statistical census of the unseen. The future Vera C. Rubin Observatory will take this further. It'll image billions of galaxies to make the most detailed dark matter map we've ever seen. Weak lensing doesn't need a brilliant foreground object. It uses the universe itself as a lens. Every distant galaxy is a tiny probe. Its distorted shape is a data point in a grand equation that solves for all the mass between it and us. It confirms the cosmic web not by the galaxies that light it up, but by the silent warping of the light traveling through its dark channels. So we move from the dramatic arcs to a universe-wide whisper, a statistical sigh that reveals the shape of the darkness. But if we can map its shape that precisely, then the next question is right there. What is this stuff actually made of? There's that quiet statistical evidence, the framework in the background. But the strongest case for dark matter came from a war in space. A huge collision seen far away, two galaxy clusters, each with hundreds of galaxies, hitting each other at millions of miles an hour. They call it the bullet cluster. That's the seventh way to see what's not there. It was a natural experiment, just enormous, and in that crash, the different parts of the clusters acted completely differently. Most of the normal matter in these clusters, the atomic stuff, it isn't in the stars. It's a gas, incredibly hot and thin, filling the space between the galaxies. This gas is so energetic it glows in X-rays, and when the clusters collided, that gas did what any particles would do. It interacted. It slowed from friction, piling up right in the middle of the wreck. Telescopes like Chandra saw it perfectly, a bullet-shaped shockwave of glowing, searing gas at the heart of it. But the galaxies themselves, and something else much more massive, they told another story. The galaxies, these huge collections of stars so far apart, they're like swarms of bees. When two swarms pass through each other, the bees almost never hit. The galaxies and the mass shown by gravitational lensing, they just sailed right through the chaos. They kept going, leaving that bright, slowed-down gas behind. That's the key separation, the map from gravitational lensing, which shows where the mass actually is. It didn't stay with the glowing X-ray gas. It stayed with the galaxies. Most of the mass didn't collide. It passed through the other cluster's mass without slowing, without glowing, without any interaction except gravity. It's like watching two clouds, one of smoke and one of birds, collide in the wind. The smoky gas, the ordinary matter, it mixes and tangles in the middle. But the birds and some invisible, heavy component, they fly straight through and come out the other side. The bullet cluster shows you, in one picture, that what creates gravity isn't the stuff that glows. It's something that passes through itself and through us completely untouched. This cosmic wreck is a forensic snapshot. It rules out the idea that we've just got gravity wrong. If modified gravity were the answer, the gravitational effect would be centered on the visible matter, the gas and the galaxies, but it's not. The gravity is with the galaxies, away from the gas. The only explanation that fits is a form of matter that's dark, that feels gravity but not the electromagnetic force. It doesn't shine, it doesn't bump into itself. It just is, and it shapes everything. So we've seen its shadow in lensing, heard its echo in the ancient light, and now we've watched it pass through a cosmic catastrophe untouched. That leads to a central question. If it's so common and so ghostly, what could it even be made of? That collision showed us dark matter's ghostly nature. But to map its delicate threads, you need a different kind of light, not from a galaxy, from a cosmic lighthouse, a quasar. These are the brilliant cores of ancient galaxies, powered by supermassive black holes. Their light is so intense it can be seen across the universe, and on its journey to us, that light passes through everything. It becomes a probe, a backlight illuminating the universe's hidden gas. This is the Lyman-Alpha forest, our eighth way to trace the invisible framework. Think of it like this. You're in a dark forest. Far ahead, you see a single, powerful searchlight shining through the trees. You don't see the trees themselves directly, but you see the shadows they cast against that brilliant beam. Each tree creates a specific, dark silhouette in the light. Now replace the forest with the vast, mostly empty space between galaxies. Replace the searchlight with a distant quasar, and replace the trees with clouds of the simplest element in the universe. Neutral hydrogen gas. As the quasar's light travels for billions of years, it passes through these diffuse hydrogen clouds. Hydrogen atoms are picky. They only absorb light at one very specific wavelength, the Lyman-Alpha line. So when astronomers take the quasar's spectrum, they don't see a clean rainbow. They see a forest, a dense thicket of thousands of dark absorption lines. Each one is a fingerprint from a single cloud of hydrogen that the light passed through. And here's the crucial part. Those clouds aren't random. They trace the cosmic web. The hydrogen gas, pulled by gravity, settles into the filaments and knots of the dark matter framework. Where the dark matter is densest, the gas is densest. So the pattern of the absorption lines, how close together they are, how deep they are, is a direct map. It reveals the clumpiness of the gaseous universe on scales far smaller than a single galaxy. By studying this forest in the light of many quasars, astronomers can reconstruct the three-dimensional distribution of this intergalactic gas. And since the gas follows the gravity of dark matter, they're indirectly charting the finest filaments of the dark matter web itself. It's like using a network of distant spotlights to create an X-ray of the cosmos's skeleton. This technique probes the universe's framework at a resolution other methods can't match. It reveals the delicate webbing that connects all the larger structures. So from the violent proof of a cluster collision, we move to the subtle, forensic analysis of absorbed light. The Lyman-Alpha forest shows us that even the empty spaces aren't truly empty. They're threaded with faint gas, and that gas paints in shadow the precise contours of the darkness that holds it all together. If we can see the gas that fell into the dark matter's grip, what about seeing the moments when that dark matter might have briefly revealed itself in a flash? The Lyman-Alpha forest maps the faint gas, but to weigh the heaviest knots in the cosmic web, you need the giants, the galaxy clusters. Their number and how that number has changed is our ninth way to find the invisible framework. It's a census of the largest structures. Galaxy clusters are the end point of gravitational collapse. They're the most massive things still held together by their own gravity. A single cluster can have thousands of galaxies, all moving through a sea of dark matter and a gas so hot it glows in X-rays. How these titans form isn't random. It comes from the initial conditions in the cosmic microwave background, and then a battle between two invisible forces. Gravity is on one side. The dark matter provides the scaffolding, and gravity pulls more matter into the densest knots. It wants to build. On the other side is dark energy. As the universe expands, dark energy acts like a cosmic repulsion. It makes it harder for gravity to pull things together across vast distances. It wants to smooth everything out. The rate clusters form over billions of years is sensitive to this tug of war. If dark matter were more abundant, gravity wins more easily. We'd see more huge clusters and see them forming earlier. If dark energy were stronger, it would have slowed structure formation sooner. There'd be fewer of these giants. So astronomers do a head count across time. They look into deep space, which is looking back in time, and they count clusters. They find them in different ways. By the X-ray glow of their hot gas, by the subtle distortion their gravity causes in the cosmic microwave background, the Sunyaev-Zeldovich effect, and by seeing the congregations of galaxies in optical surveys. By comparing how many clusters there are today to when the universe was half its age, they get a timeline of structure growth. The data tells a story. For the first several billion years, gravity was in charge. Clusters formed readily, but then, around 5 or 6 billion years ago, something changed. The formation of new giant clusters began to slow. The Census shows a universe where the initial rush of building is now being suppressed, gently but firmly. This isn't just counting, it's taking the temperature of the cosmos. Too many ancient clusters would break our models. Too few would mean a different recipe. The observed numbers fit. A universe of about 5% ordinary matter, 27% dark matter, 68% dark energy. The cluster abundance is a bulk measurement. It confirms the entire cosmic ledger from the microwave background and other probes. It means the invisible framework had a growth spurt, and now its expansion is guided by a more mysterious force. We've mapped its shape and traced its gas, but counting its greatest achievements gives us the history of its power. And if we can count the giants, what happens when we listen to the echoes of their most violent mergers? Counting giants gave us a history, but to watch the framework move, you have to look at the traffic. Those 3D maps of the cosmic web, they use a proxy for distance. Redshift, the stretching of light from the expansion. It's a brilliant tool, but it has a flaw, a revealing one. The 10th way to see the framework is redshift space distortions. It shows gravity actively working. Think of a siren, you know the sound. An ambulance comes toward you, the pitch is higher. It goes away, the pitch drops. That's the Doppler effect. Light does that. A galaxy coming toward us has its light compressed, shifted blue. A galaxy moving away has its light stretched, shifted red. Now, the main reason for the redshift is the expansion. That's the smooth background. But on top of that, every galaxy has its own local motion, its peculiar velocity. And that motion is from one thing, gravity, the pull of the massive dark matter around it. So when we plot a galaxy on the map, we use its total redshift to get a distance. But if that galaxy is falling, say, toward a big cluster, that motion adds a little extra redshift. The map puts it slightly farther away than it really is. And a galaxy falling toward us from something distant would look slightly closer. Now picture a vast filament of the web. Galaxies are flowing along it, streaming toward the dense clusters at the ends. In real space, that filament is a straight, thin line of galaxies. But in the redshift map, it looks distorted. The galaxies falling along our line of sight appear stretched. The ones moving across our line of sight are fine. So that straight filament in real space looks squashed and elongated in the map. It looks like a finger pointing right at us. By measuring this squashing the redshift space distortions across millions of galaxies, they can do something. they can measure the strength of gravity on the largest scales. They can calculate how fast structures are growing. Are galaxies streaming into clusters faster than we thought? Is the web tightening more slowly? This growth rate is a critical test. It tells us if gravity works exactly as Einstein said over these distances, and it tells us about the dark matter itself. Is it cold and slow, letting structures form from small to large? The observed growth rate from these distortions supports that model. It shows the framework isn't static. It's a dynamic, evolving landscape, rivers of galaxies flowing down the gravitational slopes of dark matter valleys. We're not just mapping a skeleton, we're taking its pulse, watching the universe gather itself together, piece by invisible piece, under the silent pull of the unseen. That pulse from galaxy flows, it's a living signal, but there's another kind of ghost, a colder one. It's stamped onto the oldest light we can see. This 11th way to trace the framework, it uses the cosmic microwave background. Not as a fossil, as a backlight. It's called the Sunyaev-Zeldovich effect. You picture the CMB as this vast, uniform wall of ancient light, and then you put a massive galaxy cluster in front of it. That cluster isn't just galaxies. It's filled with this incredibly hot, thin gas, so energetic its electrons are moving almost at light speed. So when the cold CMB photons from the dawn of time, they travel through this hot gas. And something happens. Those low-energy photons, they collide with the super-fast electrons. It's like a slow marble hitting a speeding bullet. The electron gives the photon a kick. A huge energy boost. That process is inverse Compton scattering, and the result is a distinct signature. In the specific microwave frequencies we look at, the cluster leaves a shadow. A slight cold spot in the CMB right there. It's not that the cluster is blocking the light. It's that the interaction scatters the photons away from our line of sight. It creates a tiny temperature dip. The power of this method is its purity. It finds clusters based purely on their mass, specifically the mass of that hot gas. It doesn't matter how bright the cluster's galaxies are. It doesn't matter how far away it is. The imprint on the CMB is the same. So this gives astronomers a mass-selected catalog. A list of the universe's largest nodes, from the nearby giants to the most distant, faint ones just beginning to form. It's a direct way to find the heaviest knots in the dark matter web. The places where gravity has gathered the most material over all of cosmic time. And by comparing these SZ effect clusters with maps from optical surveys with X-ray telescopes, you get a complete picture. You confirm the dark matter halos are there, and you measure how much ordinary matter in the form of that searing gas has been pulled into its grip. This ancient light, traveling for over 13 billion years, it acts as a universal screen, and every massive cluster paints its own silhouette on it. A shadow cast not by darkness, but by the fierce heat of a universe gathering itself into structure. A shadow on the ancient light shows the heaviest knots. But to use those knots as a precision instrument, you need a cosmic stopwatch. That's the 12th way, strong gravitational lensing time delays. It turns a quasar's flicker into a fundamental measurement. Sometimes the alignment is perfect. A single, distant quasar sits almost directly behind a massive galaxy in the foreground. The galaxy's gravity bends the quasar's light. But instead of a smeared arc, it creates multiple distinct images. You get 2 images or 4, or even a perfect Einstein ring, all from one object. The light for each image takes a different path around the lens. One path might be slightly longer, or it travels through a deeper part of the gravitational well where space-time is more warped. In Einstein's universe, that warping affects time, so the light in each path doesn't just travel a different distance, it experiences a different travel time. Imagine 2 runners. They start from the same point, heading to the same finish line. One takes a flat, direct road, the other goes over a steep hill. They're both running at the same speed, the speed of light, but the one going over the hill arrives later. That's the time delay. Quasars flicker and flare over months or years. Astronomers watch. They see a bright flare in one image of the lensed quasar. Then they wait. Weeks or months later, sometimes years, they see the exact same flare appear in another image. That measured gap is the time delay. It's a direct readout of the path's geometry. But to turn that delay into a cosmic measurement, you need a model. You need to map the gravitational landscape of the lensing galaxy. That means modeling its visible stars and the shape and density of its dark matter halo. The time delay is sensitive to this. By adjusting the dark matter model until the predicted delays match the observed ones, astronomers solve for the mass distribution. They're using the flickering quasar as a probe to weigh the invisible halo. Once they have that precise mass model, they can do something else. They can calculate the absolute physical scale of the system. They know the time delay. They know the speed of light. From that, they can derive the distance to the quasar and the lens independently. And that lets them measure the Hubble constant, the rate of the universe's expansion, in a way that's completely independent of other methods. It's a chain of reasoning. A flicker in a distant quasar split by an invisible halo of dark matter becomes a stopwatch. That stopwatch measures the geometry of space-time. It gives us a number for how fast the cosmos is growing. This method ties the properties of local dark matter structures, the framework of galaxies, to the largest scale fate of the universe. We're using the hidden architecture as a calibrated lens to read the cosmos's most fundamental dial. The flickering quasars gave us a cosmic stopwatch. But to test the dark matter idea in its simplest form, you need a different kind of laboratory, a smaller one, a quieter one. That's the 13th way. The dynamics of dwarf galaxies, these tiny, faint satellites that orbit giants like the Milky Way, they only have a few million stars, sometimes less. And that's the point. They are dark matter's purest experiments. In a big spiral galaxy, the gravity you feel is a complex mix, billions of stars, vast clouds of gas, and the dominant dark matter halo. But in a dwarf, the ordinary matter is almost an afterthought. There's very little gas, very few stars, so the gravitational field, the thing holding these wispy collections together, is overwhelmingly the dark matter halo. It's like trying to understand the shape of a magnet by watching iron filings. If you throw in other metals, the picture gets messy. But if you use only the finest iron dust, the pattern becomes clear. Dwarf galaxies are that fine iron dust for gravity. By measuring the motions of just a handful of stars inside a dwarf, astronomers can map the dark matter at its core with precision. These measurements give some of the tightest constraints on what dark matter can be. They test the cold dark matter model on the smallest scales, and here the model faces puzzles. The first is the missing satellites problem. Simulations of a Milky Way-sized dark matter halo predict it should be swarmed by thousands of tiny dark matter subhalos, the seeds for dwarf galaxies. But we only see dozens of actual dwarfs. Where are the rest? The likely answer involves star formation physics. Maybe most of those dark subhalos never gathered enough gas to light up. They remain completely dark, invisible islands of pure dark matter orbiting our galaxy. The second puzzle is more subtle. It's called the core cusp problem. The simulations predict dark matter halos should have a steeply rising density toward their centers, a cusp. But the observed motions of stars in many dwarfs suggest the dark matter density is more constant in the middle, a soft core. This could mean our understanding of dark matter's microscopic properties is incomplete, or it could mean that violent bursts of star formation in the dwarfs past blew out gas, and the shifting gravity smoothed out the dark matter core. These tiny, faint galaxies are not cosmic afterthoughts. They are our most sensitive probes. Their quiet dynamics ask the hardest questions. forcing us to refine our picture of the invisible particle. If the grand cosmic web is dark matter's masterpiece, then these dwarfs are the fine brushstrokes where its true nature is most clearly revealed and most puzzlingly revealed. Deep in a galaxy cluster, there's a ghost, a faint, uniform glow. It hangs in the huge spaces between the galaxies. That's intra-cluster light, the 14th way we map the invisible framework. It's not light from gas, it's the shine from countless individual stars, stars that have been torn from their galaxies. In the dense core of a cluster, galaxies don't just drift. They interact, they tug and pull as they swing by in this slow cosmic dance. And during these close encounters, the tides can rip stars right out of a galaxy's outer regions. These orphaned stars get flung into the void. They become wanderers bound not to any single galaxy, but to the gravity of the whole cluster. Over billions of years, this process builds up. The combined light of all these lost stars creates a soft background glow. It's incredibly faint, often over 1,000 times dimmer than our night sky. To see it, astronomers need extremely sensitive cameras on the largest telescopes. They have to carefully subtract the light from every known galaxy and star. What's left is this phantom map, and its shape is the clue. The distribution of this intra-cluster light isn't random. It settles into the contours of the cluster's gravitational potential. It fills the basin of dark matter like a luminous mist settling into a valley. Because the gravitational pull is dominated by the invisible dark matter halo, this ghostly glow traces its shape. It reveals the depth and extent of the halo, even in regions beyond where galaxies are found. By mapping this faintest glow, astronomers can chart the dark matter framework in a new way. It uses the casualties of cosmic collisions, the stars stripped by gravity, to illuminate the very source of that gravity. It turns the aftermath of violence into a delicate tool. This intra-cluster light is a testament to the dynamic, often destructive history of these giant structures. It shows the framework isn't static. It's a landscape shaped by relentless gravitational encounters. And the stars caught in the crossfire become a permanent record. They paint the silhouette of the darkness that orchestrated it all. That intra-cluster light, it's a kind of ghost. It shows where collisions happened, but the framework, it was shaped by another ghost too, one that was there before atoms. It's a sea of particles. They're so elusive, they pass right through the planet, like it isn't even there. That's the cosmic neutrino background, the 15th way to see the framework. Right after the Big Bang, the universe was dense, it was hot, and it created trillions of these particles, neutrinos. They've been streaming through space ever since. A relic from the very start. For a long time, we thought they had no mass, that they moved at light speed. But now we know they have a tiny mass, almost immeasurable. And that changes things because each neutrino's mass is minuscule, but the number of them is staggering. There are over 300 in every cubic centimeter of space. Right here, right now, and that adds up. This neutrino sea, it contributes to the total matter density. It's a known part of the inventory, elusive but known. But their real influence is on the early universe. Neutrinos interact so weakly, they don't clump under gravity, not like dark matter. Instead, they stream. They're cosmic smoothing agents. In the first moments, their motion washed out the tiniest density fluctuations. They created a neutrino fog. It suppressed the formation of the smallest structures. We see the echo of that today in our maps of the cosmic web. The distribution of galaxies shows a slight deficit, a lack of the tiniest clusters. That's the signature of the early smoothing. To get our models right for the cosmic microwave background, for the large-scale structure, we have to account for this fog. It's a subtle effect, but it's there. And it means the invisible framework isn't one thing. It's a layered architecture. Dark matter provides the main scaffold, the primary gravity, but woven through it is this sea of ancient particles. whispering, and they soften the edges on the smallest scales. They are the oldest travelers, and their faint imprint, it's a reminder. Even the most ghostly things leave a mark on the shape of everything. Those neutrinos smoothed out the smallest scales, but on the largest scales, the universe is still in motion. Galaxies aren't just passengers on expanding space. They have their own motion, a peculiar velocity. That's the 16th method, studying cosmic flows. The main motion we see is the Hubble flow, the expansion of space itself, stretching light, making distant galaxies seem to rush away. But on top of that smooth recession, every galaxy has a local drift. It's being tugged by the gravity of its neighbors, by the immense pull of a nearby supercluster, or pushed by the emptiness of a vast void. These motions are like a circulatory system, rivers of galaxies, thousands of them, streaming down the gravitational slopes of the dark matter web. To map this flow, you need two independent measurements for a galaxy. First, its true geometric distance, not from redshift but from a standard candle. Something like a Cepheid variable star where we know its intrinsic brightness. You compare how bright it appears to how bright it truly is, and you get a direct distance. It's like knowing exactly how far away a lighthouse is by the known wattage of its bulb. Second, you measure the galaxy's redshift. That tells you how fast the expansion of space is carrying it away. Now here's the key. If the galaxy were only moving with the Hubble flow, these two numbers would match perfectly. The distance from the standard candle and the distance inferred from the redshift would agree. But they rarely do. There's almost always a discrepancy. That difference is the peculiar velocity. It's the extra push or pull from local gravity. If the redshift distance is greater than the true distance, the galaxy is being pulled toward us by some massive structure behind us. If it's less, the galaxy is being pulled away toward something massive in front of it. By doing this for thousands of galaxies across our local universe, you don't just get individual motions. You see a pattern, a coherent flow. Our entire galactic neighborhood, the Milky Way and our local group, we're all being pulled in a specific direction, toward a colossal concentration of mass hundreds of millions of light years away, known as the Great Attractor, and that attractor itself is being pulled toward something even larger. These bulk flows are a direct gravitational assay. They let astronomers do a cosmic accounting. By tracing the streams of galaxies back to their sources, they can calculate the total mass that must be doing the pulling. It's like standing in a river and feeling the current. From the strength and direction of the flow, you can estimate the size and slope of the watershed upstream. The map that emerges confirms the dark matter framework on the largest scales. The flows point directly toward the densest knots and filaments of the cosmic web. They reveal the gravitational landscape in motion. We're not just mapping a static skeleton, we're feeling its pull. Watching entire clusters of galaxies slide, like beads on a string, along the invisible threads woven through the universe from the beginning. These cosmic flows map the large-scale pull, but the most intimate clues are right here in our own galactic neighborhood. Faint rivers of stars, almost invisible against the black, they arc across the halo of the Milky Way. They're called tidal streams, our 17th way to see the invisible architecture. They're the archaeological record of our galaxy's violent past. When a small dwarf galaxy, or a dense globular cluster, gets too close to a giant like ours, the tidal forces stretch it out. The difference in gravity from one side to the other, it pulls the object apart into a long, thin stream of stars. It follows an orbit like a celestial breadcrumb trail. We see these streams now, the Sagittarius stream, the Orphaned stream. They're the ghosts of galaxies being digested, but they're more than fossils, they're dynamic probes. The exact shape of a stream, the speed of the stars within it, these details are sensitive, incredibly sensitive to the gravitational field they move through. And that field is dominated by the dark matter halo of the Milky Way. Think of it like dropping glitter into a basin of clear, thick syrup. The way the glitter spreads will map the exact contours of the basin. Every bump and dip, the tidal streams are that glitter. By tracking their paths, astronomers can do galactic archaeology. They can reconstruct not just what was swallowed, but the precise shape of the mouth that did the swallowing. Is our dark matter halo smooth and spherical, or is it lumpy, filled with countless smaller subhalos of dark matter, like the simulations predict? A smooth halo would shepherd a stellar stream into a narrow, coherent band. But if the halo is clumpy, the gravitational kicks from passing dark matter subhalos would perturb the stream. They'd stir it up, creating gaps and kinks in the stellar river. Searching for these subtle distortions is like looking for footprints of invisible creatures passing through a field of tall grass. The current data is tantalizing. Some streams appear remarkably smooth, others show possible signs of disruption. This detective work is ongoing, a meticulous effort to read the fine print in the dark matter's contract. It turns the carnage of ancient collisions into a precision tool. Every stream is a story of a small galaxy's end, written in the language of gravity on the dark page of the halo. By reading these stories, we're not just learning about our galaxy's history, we're testing the fundamental nature of the dark matter particle itself. On the scale of our own cosmic backyard, stellar archaeology reads the fine print of our own halo, but there's another imprint, even more subtle. It asks you to look at the oldest light and the largest structures together. That's the 18th way, the integrated Sachs-Wolfe effect. It measures the fading of the universe's deepest gravitational wells. Think of the cosmic web as a landscape. Valleys and hills. The valleys are the dense superclusters where gravity is strongest. The hills are the vast, empty voids. A photon from the cosmic microwave background, traveling for billions of years, is like a marble rolling across this terrain. It rolls down into a deep valley, a gravitational potential well, and it gains energy that makes it appear slightly hotter. Then it climbs back out, and it loses that energy, cooling back down. In a static universe, the net effect would be zero. Gain and loss would balance, but our universe isn't static. It's expanding, and dark energy is causing that expansion to accelerate. That changes the landscape itself. The deep gravitational valleys, the potential wells of the superclusters, are slowly becoming shallower over cosmic time. They are fading, so picture that marble again. It rolls down into a valley, but while it's crossing that valley, the valley floor itself is rising. The photon doesn't have to climb out of as deep a hole as it fell into. It loses less energy on the way out than it gained on the way in. The result is a tiny net gain, a minuscule heating, and conversely, a photon crossing an expanding void, a gravitational hill, experiences a net cooling. This creates a specific pattern, a predicted one. There should be a faint correlation between the hot and cold spots we see in the cosmic microwave background and the locations of the largest superclusters and voids in the nearby universe. It's an incredibly small signal buried in noise, but by cross-referencing the most precise CMB maps, like from Planck, with three-dimensional maps of millions of galaxies, astronomers have found it. That faint whisper of correlation is the integrated Sachs-Wolfe effect. It's a direct signature, not just of the dark matter framework, but of its evolution. Its evolution under the influence of dark energy. It shows the cosmic landscape is not frozen. The greatest structures, the superclusters that took billions of years to assemble, are slowly being pulled apart. Their gravitational grip is weakening as the universe stretches. This effect ties the first light to the last structures. It uses the fading echo of primordial gravity to confirm the force. The force that will ultimately define our cosmic future. The fading of those cosmic hills and valleys shows how the framework is evolving now, but to see its first moments, you need a different telescope. One that listens to a whisper from before the stars, a whisper at 21 centimeters. That's the 19th way, 21 centimeter line cosmology. It looks into the universe's dark ages. After the cosmic microwave background was released, the cosmos went quiet for hundreds of millions of years. No stars, no galaxies, just a warm, expanding fog, neutral hydrogen gas. But that gas has a signature, the hyperfine transition. The spin of a hydrogen atom's electron can flip. Relative to its proton, that tiny quantum jump releases a photon at a very specific wavelength, 21 centimeters, a radio wave. That faint radio hum filled the whole universe during the Dark Ages. But it wasn't uniform. The hydrogen gas wasn't spread evenly. It had already started to pool into the subtle gravitational wells the dark matter framework made. Where the dark matter was denser, the hydrogen gas was denser and slightly warmer. These tiny differences in density and temperature left specific fluctuations on the 21 centimeter signal. Future observatories like the Square Kilometre Array want to do something extraordinary, map this signal in 3 dimensions across cosmic time, because the expansion of the universe stretches the wavelength. The observed frequency tells you how old the signal is, so by tuning across a band of radio frequencies, they can make a movie, a 3-dimensional map of the hydrogen fog as it evolves. From just after the cosmic microwave background, all the way through the cosmic dawn when the first stars finally switch on, this map would be a direct image of the dark matter framework at work in its purest form. For the first time, we'd see the distribution of all matter, driven by dark matter's gravity. Without the glare of starlight, it would show the first seeds of the cosmic web as they begin to condense out of the primordial darkness. The fluctuations in this ancient radio light would test our dark matter models. With a new precision, they could reveal if dark matter particles interacted with each other or with the hydrogen gas in subtle ways, leaving a fingerprint on this universal signal. This is the ultimate archaeological dig. It goes deeper than the cosmic microwave background. It probes the era when the invisible framework was the only architect. Quietly gathering the raw material for everything to come, it promises a view of the universe, written not in light, but in the quiet spin of hydrogen atoms. Tracing the contours of the darkness that would one day give birth to the stars. That ancient radio hum mapped the universe before the stars. To feel the framework move in real time, you need a different signal. Something that shakes space. The 20th way is gravitational wave standard sirens. It uses ripples from the most violent events to build a new ruler. For over a century, light was our only messenger. Then in 2015, LIGO felt it, a tiny tremor in spacetime. A gravitational wave from 2 black holes colliding over 1 billion light-years away. That opened a new sense. We can hear the universe now, and some of these events, especially mergers of 2 neutron stars, they're not just a gravitational thump. They often come with a flash, a brilliant burst of gamma rays, then a fading glow across all wavelengths. This pairing is the key. The gravitational wave signal gives something unique. It tells you the absolute distance to the event. From the shape of the wave, the chirp, you can calculate the intrinsic strength of the collision. Compare that intrinsic strength to how faint the signal is when it reaches us, and you get a direct distance. No cosmic ladder, it's like hearing a siren. From its known pitch and how faint it sounds, you can tell exactly how far away the ambulance is. That's why they're called standard sirens. Now, if telescopes also see the flash, they can measure the redshift of the host galaxy. That gives the speed of cosmic expansion at that location. Put the two together, the direct distance from the gravitational wave and the redshift from the light, and you have a single, clean measurement of the Hubble constant. It's a completely independent check on the expansion rate, free from the assumptions other methods carry. but the power goes beyond a single number. As detectors become more sensitive, we'll hear these cosmic collisions from deeper in the past. By counting the population of mergers across cosmic time, we can trace how the rate of these violent events has changed. That rate isn't random. It depends on the underlying distribution of galaxies, which is shaped by the dark matter framework. In a universe where structure formed earlier, mergers would have been more common in the past. In a universe smoothed by dark energy, the rate changes in a specific way. The gravitational wave background, the collective hum of countless unresolved mergers, will become a new probe. It will sense the large-scale distribution of matter through its most extreme interactions. This method adds a dynamic, auditory channel to the cosmic survey. We're no longer just looking at the framework, we're listening to it ring. Every chirp from a colliding neutron star is a timestamp and a distance marker, etched into space-time, helping us chart the invisible landscape that orchestrates the universe's most dramatic dances. Gravitational waves let you hear the framework ring, but to get a full census of its mountains and valleys, you need a different map. The 21st way is weak lensing peak statistics. It counts the invisible mountains. When you make those mass maps from the shearing of galaxy shapes, you're not just seeing a smooth distribution. The map has texture. It has peaks, regions of high convergence where the dark matter is densest. Each peak is a massive dark matter halo. Some of these peaks line up with galaxy clusters we already know. But many don't. They're mountains without a crown, halos massive enough to warp light, but that haven't gathered enough gas and stars to shine as a traditional cluster. Or maybe they never will. They're pure dark matter structures, and by counting these peaks, and not just counting them, but sorting them by height, by significance, cosmologists can do something. They can take a census of the entire population of dark matter structures, from the mountain ranges down to the hills. This statistical approach is sensitive. It tests the models of how structure forms. Does the number of peaks at a certain mass match what cold dark matter simulations predict? The internal density profile of a halo matters. Whether it has a sharp cusp or a soft core affects how it appears as a peak. A halo with a dense, compact core creates a sharper, more significant peak. A diffuse one creates a broader, subtler signal. So by analyzing the population of peaks, their abundance and their shapes, you get a dual measurement. You learn how many halos exist at different masses, and you learn about their internal architecture. It's a way of taking the cosmic landscape, revealed by warped light, and turning it into a histogram. A bar chart of the invisible. This method doesn't rely on light emitted by the structures. It relies solely on their gravity. It promises to find the dark matter halos that other surveys miss. The ones that are truly dark, and in doing that, it completes the map, not just of the glittering cities in the cosmic web, but of every town, every village, every solitary homestead in that vast, invisible country. Peaks on the mass map show where dark matter gathers, but you have to look at the valleys too, the cosmic voids. That's the 22nd way to trace the framework. Weighing the emptiness, those 3D maps of the cosmic web, they show the filaments and clusters, but they show the opposite too. Huge regions, hundreds of millions of light years across, that are almost empty. They're not perfect vacuums. A few lonely galaxies drift inside, but compared to the dense walls, they're deserts, and the shape of those deserts tells a story. About the forces that carved them, the gravity here works in reverse. Instead of pulling matter in, the void's emptiness creates a kind of negative gravity. The mass is all outside, in the surrounding walls, so galaxies near the edge of a void, they get a net push outward, away from the center. They stream toward the dense filaments. That motion and the subtle distribution of the few galaxies inside, it creates a specific density profile, a signature. By studying the shapes of many voids, how spherical they are, how sharp their boundaries, cosmologists get a complementary test. Clusters are where gravity wins, gathering mass. Voids are where expansion wins, pushing matter apart. In these low-density places, the repulsive effect of dark energy has a more noticeable impact. It can influence the void's growth, making it expand faster than the general universe. So voids become laboratories for dark energy. The hierarchy of voids, from the vast supervoids down to smaller ones, their abundance over cosmic time, it offers a unique window. A view of the negative basins in the universe's gravitational potential. Clusters show us the mountaintops of the dark matter framework. Voids show us the depths of the canyons. Mapping both gives the full topographic map. It confirms the invisible architecture isn't just a collection of mass, it's a balanced system, peaks and troughs, where even the emptiest places hold a record of the forces that shaped everything. Voids map the empty basins in that gravitational landscape, but to see the full picture, you have to listen on every channel. That's the 23rd way, multi-messenger astrophysics. It's building a unified portrait of the cosmos. For centuries, we only had one messenger, light. But light is just a narrow slice. The universe is broadcasting so much more. Modern astronomy opens the whole spectrum, from long radio whispers to violent gamma-ray shouts. And it adds new senses entirely, the tremors of gravitational waves, the silent passage of cosmic neutrinos. When you combine these different messengers from one event, you get something unparalleled. A complete story. Take a neutron-star merger. In 2017, we felt it first. A ripple in space-time, a gravitational wave chirp that lasted about 100 seconds. Then telescopes saw the flash, a short gamma-ray burst, then a kilonova, this glowing cloud of newly forged heavy elements, gold, platinum. That single event, observed through gravity and light, answered questions in an instant. It confirmed that neutron-star collisions are factories for the universe's heavy elements. It gave us a new, direct way to measure the expansion rate of the universe. And it tested Einstein's theory of gravity in the most extreme regime. That's the power of multiple messengers. Each one carries different information. Light tells you about temperature, composition, magnetic fields. Gravitational waves tell you about masses, spins, the pure dynamics of space-time. When you bring them together, you cross-check reality. You calibrate your instruments against each other. You build a model that's consistent, robust, far harder to challenge. For our search of the invisible framework, this holistic approach is essential. It means our understanding isn't built on a single, potentially biased line of evidence. The dark matter halo we infer from galaxy motions has to agree with the halo we map through gravitational lensing. The cosmic web traced by galaxies has to match the web implied by the Lyman-Alpha forest in quasar light. And the history of structure growth from the cosmic microwave background has to align with the history written in the cluster census. Multi-messenger astrophysics is the ultimate convergence. It's the moment we stop seeing the universe as a collection of separate puzzles. We start seeing it as a single, interconnected system. Every signal is a piece of the same narrative, from the faintest radio wave to the most profound space-time shudder. A narrative about how an invisible framework of dark matter gathered the raw material of the cosmos, and how a mysterious dark energy began to shape its ultimate fate. With each new messenger we add, the portrait comes into sharper focus, more consistent. We're not just looking at the universe anymore, we're listening to it, feeling it, beginning to understand its full, hidden architecture. The first galaxies weren't just islands of light. They were the first beacons, and they were switched on inside an invisible architecture. To see them is to look back to the very edge of our cosmic timeline. With the James Webb Space Telescope, we're now witnessing those first lights in the dark. This is our 24th way to uncover the invisible framework. The formation of high-redshift galaxies. These aren't the majestic spirals we know today. They're infant systems, we see them as they were just a few 100 million years after the Big Bang. Their existence and their surprising properties are a direct report from the earliest dark matter halos. Our models say structure formed from the bottom up. Small dark matter halos coalesced first, then they merged to build larger ones. These halos were the gravitational wells. They gathered the first clouds of primordial hydrogen gas. Only when enough gas pooled and cooled and condensed could the first stars ignite. So every one of those faint, ancient smudges of light in Webb's deepest images is more than a galaxy. It's a signpost. It marks the location of a successful dark matter seed, one that grew large enough, fast enough to light up. The properties of these infant galaxies are a precise test. How bright they are tells us about the efficiency of star formation inside those early halos. How many we see at different epochs tells us the rate at which halos were reaching the critical mass to form stars. And some of these galaxies appear shockingly massive and bright, far earlier than many simulations predicted. This could mean our understanding of those first stars is incomplete. Or it could be telling us something about the dark matter itself. Perhaps the particles were slightly warmer or interacted in ways that altered the timing. Each new distant galaxy Webb finds is a data point. It helps us refine the story of how the invisible framework laid down in the first instant began to gather the luminous world we see today. We are watching the universe's childhood documented in starlight, and every new image confirms the dark matter blueprint was already in place, silently setting the stage for everything to come. The faintest galaxies show us where the framework first gathered light, but to know what that framework is made of, you have to leave the cosmos. You go into the laboratory. The 25th way to uncover the invisible framework isn't an observation. It's an experiment, a direct hunt for the particle itself. Searches for weakly interacting massive particles for actions. That's a frontier of pure physics where the cosmic mystery meets the precision of an underground detector. For decades, the leading candidate has been the WIMP. A weakly interacting massive particle. It fits the cosmic evidence beautifully. It would be heavy, slow-moving. It would interact only through gravity and the weak nuclear force. That explains why it doesn't shine, why it doesn't bump into ordinary matter often. Billions could be passing through you every second, completely unnoticed. To catch one, you need to go deep, miles underground into old mines beneath mountains. You shield the experiment from cosmic rays, from natural radioactivity. You create the quietest environment on Earth, and then you wait. You use ultra-pure crystals, tanks of liquid xenon, chilled to extreme temperatures. You watch for the tiniest signal, a flash of light, a minute amount of heat, a single electron knocked loose, the signature of a dark matter particle, after its long journey across the galaxy, finally bumping into an atomic nucleus here on Earth. The results so far have been silence, exquisite, profound silence. But in science, a null result isn't a failure. It's a map of what is not there. Each experiment that sees nothing rules out a vast range of possibilities. It tells particle theorists to cross whole families of potential WIMP off the list. The parameter space shrinks, the target narrows. Meanwhile, another hunt pursues a ghost of a different kind. The action, theorized to be billions of times lighter than an electron. This particle would be more like a wave than a discrete bullet. To find it, you don't go underground. You build a powerful, precise magnetic field. The idea is that in the presence of this field, an action might very rarely convert into a microwave photon. It's like tuning a cosmic radio to a frequency no ordinary matter produces, listening for a whisper that would signal a universe filled with a cold, wave-like dark matter. These laboratory frontiers are where the story comes full circle. The astronomical evidence tells us the dark matter framework exists. It maps its shape, measures its gravity. The particle experiments tell us what it could possibly be. Each null result from a detector feeds back into the cosmic models. It refines the theoretical possibilities for the substance that shapes galaxies. It bridges the gap, the immense gap between the gravitational pull of a distant cluster and the potential flicker in a vat of liquid xenon a mile beneath the ground. This is the quiet, patient work of defining a ghost by everything it is not, bringing us closer to the day when a signal, however faint, finally breaks the silence. Deep underground, the detectors are silent, but out in space, time is being measured by the oldest clocks we have, the stars, not the bright, short-lived ones. The quiet, fading ones in certain ancient galaxies. That's our 26th way to see the invisible framework, cosmic chronometers. They use the aging of the oldest stars to read the expansion history directly. In the dense cores of massive elliptical galaxies, something happened long ago. A huge burst of star formation used up all the gas, and then it stopped. These galaxies became passive. They don't make new stars anymore. What's left is a vast population of old, red stars, all born around the same ancient time, now slowly cooling and fading together. Their collective light in a spectrum tells a story. The absence of certain blue stars, the presence of features from older, redder stars. It lets astronomers estimate the age of the whole population. It's like looking at a large community where everyone is retired. From the demographics, you can tell when that community's active growth ended. Now take two such passive galaxies. One is closer at a lower redshift. The other is farther at a higher redshift, so we see it as it was when the universe was younger. Measure the age of the stars in each. The difference in their ages tells you how much cosmic time passed between when the farther galaxy's light was emitted and the epoch of the nearer one. You get a direct measurement of how much time passed for a given stretch of cosmic expansion, marked by that difference in redshift. This technique, these stellar clocks, gives a measurement of the Hubble parameter throughout history, h of z. It's remarkably clean. It doesn't rely on a cosmic distance ladder. It doesn't depend on models of supernova or standard rulers. It uses stellar astrophysics and the straightforward ticking of cosmic time. The results from these chronometers weave into the same story. They confirm the expansion didn't proceed at a constant rate. The data shows a transition. An early period when expansion was slowing under the gravitational pull of all the matter, and then a shift to an era of acceleration, driven by the repulsive influence of dark energy. The aging of these quiet galaxies, these cosmic retirees, pins down the timing of that shift. It gives another independent constraint on the density of dark matter and the strength of dark energy. The invisible framework dictates the rate space stretches, and the oldest stars in the universe, by simply existing and fading, record that rate for us. They're not just inhabitants, they've become its most patient historians. Their slow burn etches a timeline onto the darkness. Cosmic clocks tick, and they measure time expanding. But to see the framework move, you have to watch the gas. That's the 27th way, the kinetic Sunyaev-Zeldovich effect. It listens for a Doppler shift in the oldest light. We had the thermal version before, where hot cluster gas scatters the CMB and leaves a cold spot. This is different. It's not about temperature, it's about motion. So take that same massive galaxy cluster, but now it's drifting. It has a peculiar velocity, a bulk flow through the expanding universe. All that hot, thin gas inside is moving with it. And when the ancient CMB photons pass through this moving cloud of electrons, they get a double shift. They get the energy kick from the heat, the inverse Compton scattering. But then, because the whole cloud is moving relative to the CMB's rest frame, the photons also get a Doppler shift. It's like a train whistle. The pitch changes if the train is coming or going. Here, the shift is in the CMB's temperature in that direction. If the cluster is moving toward us, its gas compresses the photons a little. making that patch of sky seem a tiny bit warmer. If it's moving away, it stretches them, making it seem a tiny bit cooler. The signal is incredibly faint, buried in the noise of the primordial CMB itself. Isolating it is a major technical challenge, but if you can measure it, you get something. A direct measurement of the cluster's line of sight velocity, independent of its distance. And this isn't a velocity from the expansion of space. It's the cluster's own motion from gravity. That gravity comes from all the matter around it. The pull of neighboring superclusters, the push from vast voids. So by mapping these bulk flows of gas with the K as the effect, astronomers are weighing the gravitational landscape. They're seeing how the invisible framework of dark matter, on scales of hundreds of millions of light-years, is tugging entire galaxy clusters and all their hot gas through the cosmos. It turns the cosmic microwave background into a vast screen, a screen where the streaming motions of the universe's baryonic matter are written as the faintest temperature whispers. Each whisper confirms the pull of the unseen, setting the visible universe in motion along the dark rivers of the cosmic web. These faint temperature whispers show the motion of cosmic gas. But some signals aren't whispers, they're sudden, brilliant screams, fast radio bursts, the most energetic radio flashes in the universe and the most fleeting. They last just milliseconds, but they release more energy than our sun puts out over days, and their journey to us tells a story through dispersion. That's the 28th way. Gravitational lensing of fast radio bursts. It uses these split-second signals to probe the finest threads of the web. A fast radio burst travels across billions of light-years, and its radio waves don't move through a perfect vacuum. They pass through thin, ionized gas, the stuff that fills the space between galaxies. This plasma, this warm, hot intergalactic medium, it slows the lower frequency radio waves a little more than the higher ones. The signal stretches out. That effect is called dispersion, and it leaves a fingerprint. By measuring how much the burst is stretched, astronomers can calculate the total number of free electrons it passed through along the whole path. That's the dispersion measure. It's a column density, a count of invisible particles. Now, imagine one of these brilliant bursts gets gravitationally lensed by a galaxy in the foreground. Its light splits into two paths or more. Each image takes a slightly different route through the cosmic web. One path might cut through a denser filament of that ionized gas. Another might skirt the edge of a void. Each journey imprints a different dispersion measure on its copy of the signal. By comparing these measures, astronomers can do something. They can map in detail the distribution of that invisible ionized gas along those specific lines of sight. This gas is crucial. It's believed to be a major part of the universe's missing ordinary matter. The baryons our cosmic inventory says should be there, but we haven't fully found. It's another layer of the invisible framework. Not dark matter, but the warm, diffuse plasma that weaves through the dark matter scaffold. A single lensed fast radio burst acts like a network of cosmic dipsticks. Each image probes a slightly different column of the universe, measuring the density of this elusive material. It turns a mysterious, explosive event into a precision tool for mapping. We're using the most transient signals to illuminate the most pervasive, yet nearly invisible component of the cosmic web. The architecture of the universe is written not just in mass, but in this faint, electrified fog. And now we have a way to read its contours using flashes of radio light that are here and gone in the blink of an eye. That faint, electrified fog, that's the universe's ordinary matter. Finally accounted for, but the oldest light, it holds another kind of record, not structure, pure energy. The 29th way to find the invisible framework is spectral distortions. In the cosmic microwave background, we've been treating the CMB like a perfect snapshot, a uniform glow, but its spectrum, the exact spread of energy across every wavelength, that's a master document. It tells the story of the universe's thermal history. For it to be that perfect blackbody we see, the early cosmos had to be in exquisite thermal equilibrium. Energy had to be smooth. Any big injection of energy after a certain point, any event that dumped heat into the system, it would have left a fingerprint. A distortion, a tiny bump or dip in that pristine curve. These distortions are fossilized heat from processes we can't see directly. One source could be the dissipation of those primordial sound waves. From the early universe, as they rippled through the hot plasma, they would have eventually damped, their energy dissipating as heat. That subtle heating would leave a specific mark. Another possibility involves dark matter itself. What if dark matter particles aren't completely stable? What if, very rarely, they decay? Or what if two dark matter particles annihilate when they meet? Both processes would release energy, a burst of photons or other particles that would heat the cosmic plasma. That energy injection happening across cosmic time, it would also distort the blackbody spectrum. In a characteristic way, the signature would be incredibly faint. To see it, you need instruments of phenomenal precision, designed not to map the CMB's temperature variations, but to measure its absolute spectrum. Across a vast range of frequencies, future missions are being planned for just that. Finding such a distortion would be a monumental discovery. It would open a new window into the particle physics of the dark sector. It would tell us if dark matter interacts with itself in ways beyond gravity. It would give us a timeline for when that energy was released, offering clues about the mass and lifetime of the dark matter particle. This isn't about mapping the framework's shape anymore. This is about taking its temperature, reading its energy balance sheet. The CMB's perfect blackbody is a testament to a calm, ordered infancy. Any deviation from that perfection is a clue to a moment of hidden violence or a slow, quiet decay woven into the fabric of the cosmos itself. It turns the universe's first light into a calorimeter, measuring the heat from the invisible world that built our own. The cosmic microwave background spectrum is a record of pure energy. But to understand it, you have to decode a flood of data. The 30th way we find the invisible framework isn't a telescope. It's a virtual universe built in silicon. Machine learning and cosmological simulations, that's how we test the whole story now. Modern sky surveys give you more data in one night than astronomers saw in the last century. Billions of galaxy shapes, colors, positions. In that ocean of numbers, the subtle signs of dark matter and dark energy are hidden. Finding them isn't something human eyes can do alone anymore. You need algorithms that learn, so machine learning systems are trained to spot the faint distortions from gravitational lensing across millions of galaxy images. They classify distant objects faster, more accurately. They sift through the noise to find the rare events, the statistical patterns that point to the physics underneath. That's how raw data becomes cosmological parameters. Pixels turn into insights about what everything is made of and where it's all going. But to know if those insights are true, you need a control universe. One you built yourself. That's where cosmological simulations come in. Projects like Illustris TNG, the Millennium run their Titanic. They start with a box of virtual space filled with particles that stand for dark matter, gas, and the laws of physics. They set the initial conditions from the cosmic microwave background. They put in a specific recipe: so much cold dark matter, so much dark energy, the precise strength of gravity. Then they press play on a supercomputer. For months, the simulation runs, trillions of gravitational interactions. It watches virtual dark matter clump into halos. Gas flows in, cools, forms stars. Galaxies collide and merge. Black holes grow and pour energy back. The simulation evolves this virtual cosmos over 13 billion years, from a smooth primordial soup to an intricate cosmic web. The result isn't a cartoon. It's a synthetic universe with its own billions of galaxies, each with properties you can measure, and this is the ultimate test. Astronomers take this virtual cosmos and compare it in detail to the one we actually see. Does the simulation produce the right number of giant clusters? Do its galaxies have the correct shapes, sizes, colors at different times? Does the distribution of hydrogen gas in its Lyman-Alpha forest match the shadows we see in quasar light? The simulation is a reality check for our whole theoretical framework. If a model of dark matter can't, in a supercomputer, grow a universe that looks like ours, then that model is wrong. It's a process of elimination played out across cosmic history. These virtual labs let us ask what-if questions the real universe can't answer quickly. What if dark matter was slightly warmer? What if dark energy changed strength over time? Run the simulation and see. This synthesis of big data and artificial creation brings the journey full circle. We started by observing the universe's hidden structure through 30 different lenses, from the bending of light to the timing of stellar explosions. Each method gave us a piece of the puzzle. Now, with machine learning and simulations, we assemble the final picture. We take all those pieces, feed them into a model of reality, and ask the computer to build the cosmos from scratch. The agreement we see, the way this virtual universe mirrors our own in so many details, that's the strongest evidence we have. It tells us the invisible framework isn't just a convenient story. It's a predictive, robust architecture, one that emerges inevitably from the simple ingredients dark matter, dark energy, the laws of physics evolving from the first instant to the structured, glittering cosmos we call home. The universe wrote its history in invisible ink, and we've finally learned how to read it. We're not looking at 30 separate clues. It's one story told in 30 different languages. Each method, the bending of light, the ticking of stellar clocks, is a dialect, a different way of asking the cosmos the same questions. What are you made of? How did you grow? Where are you going? And the universe, in every dialect we've learned, gives back the same answers. Those answers point to an invisible architecture. The luminous matter we see, the stars and galaxies, they're just the decorative trim. On a much larger, darker framework, this convergence is the real power of modern astronomy. It's not about one silver bullet discovery. It's the overwhelming weight of a consistent narrative, built from independent lines of inquiry that all intersect at the same conclusion. The rotation of a single spiral galaxy tells us about dark matter's local grip. The statistical shearing of a billion galaxy shapes maps its vast web. The faint afterglow of the Big Bang records its original seeds, and the unexpected dimness of distant supernova shows the dark energy now stretching that web apart. These aren't contradictory reports, they're chapters. Each chapter probes a different scale, a different epoch, a different physical effect. Gravitational lensing weighs the present-day mass. The cosmic microwave background fingerprints the infant universe. Baryon acoustic oscillations measure the expansion history, and cosmic flows feel the pull of the largest structures. When you combine them, the uncertainties shrink, the parameters lock in. We get a cosmic recipe with remarkable precision. Ordinary atomic matter, the stuff of planets and people, that's only about 5% of the total. Dark matter, the invisible gravitational scaffold, accounts for about 27%. And dark energy, the mysterious agent of acceleration, that's the remaining 68% of the cosmos. This is the lambda-cold dark matter model, the standard model of cosmology, and it didn't spring from one brilliant insight. It emerged piece by inevitable piece from this vast and varied conversation with the universe. This multi-pronged approach transforms dark matter and dark energy from speculative curiosities into the foundational pillars of our understanding. They're no longer placeholders for our ignorance. They're the active, dominant ingredients in the recipe for reality. Their effects are measured, mapped, and modeled with a precision that rivals any other branch of physics. We've moved from asking if they exist to asking precisely what they are. The framework is no longer invisible in principle. We've felt its gravity, we've traced its contours. We've heard its echoes, we've watched it shape the history of everything. The convergence of evidence paints a coherent portrait, a deeply strange one. A universe where the most familiar forces, light and matter, are just the visible embroidery on a fabric woven from shadows and propelled by a form of energy we don't yet comprehend. We started with the stars, then we learned to see the space between them, the way a billion galaxies shear, the cold whisper left over from the Big Bang. Each one is a different way of seeing, a different way of listening, and together they show us a universe where the strongest forces are the quietest. Where the most common stuff is what we can't touch. That's not a failure, it's what we figured out. We read the universe by its shadows, by how it bends light, slows time, by the old vibrations frozen into everything. So dark matter and dark energy, that invisible framework, it's not just an idea anymore, it's how reality works. It's the code. It decides how galaxies spin, how clusters crash together, how space itself stretches out into whatever's next. We've measured it precisely. We've mapped its filaments across billions of light years, watched its influence from the very beginning until now. This framework defines it all. It decided where the first stars would light up. It guides the dance of the spirals. It sets the final fate for everything we see, and the tools keep changing. The Vera C. Rubin Observatory will map the sky in detail we've never had. Gravitational wave observatories in space will listen to black holes colliding all across time. Machine learning will find patterns in oceans of data, patterns we'd never see. So the next step isn't just mapping the framework, it's understanding what it's made of, maybe catching a signal from a dark matter particle, or seeing what dark energy actually is. It changes your place in things. We're not just living in a universe of light, we're seeing a bigger architecture, a darker one, more mysterious. It was always there. We just had to learn how